Hey guys, what's up? Welcome back. We are going to go through some polar coordinates today. It should be somewhat a little bit of a review, hopefully, for most of the stuff. There's going to be some new things, hopefully, that you haven't seen before. But just to get an idea, refresh ourselves with polar coordinates, because we're going to use them whenever we talk about multivariable limits, and we're going to use them when we do double integrals in polar coordinates. So we just want to throw it in here. It's a good place to throw it in before we get into chapter 14 in the Stewart Calculus textbook. So yeah, so that's what's up. And later this week we have our first exam. I think our first exam is actually not going to cover polar coordinates. We're going to put that on the second exam. But our first exam will be all the way up through quadric surfaces, which is what we covered Friday. So this Friday, first exam, 8 a.m. I'll give you some more details on Wednesday about how it's going to go down and stuff like that. But yeah, so yeah, cool. I guess let's get started. Polar coordinates. This is Stewart Calculus 10.3. So 10.3, polar coordinates. And we're just going to review. I'm going to give you more of like a, I guess just like a geometric approach to polar coordinates to start off, and then we'll do a lot of computation stuff. You know, it's the analytic side of stuff. But really what's going on with the coordinate system is you have a flat 2D space. So flat 2D space, you know, like a plane, can be described with many coordinate systems. The most common one, of course, that you've heard of is Cartesian coordinates. And to talk about Cartesian coordinates, what you need to do is you need to specify an origin. So you specify an origin. Then you define two perpendicular axes. And their directions. And then you describe a point in Cartesian coordinates with an ordered pair. XY. And we know in Cartesian coordinates, say this is our set of Cartesian coordinates, x, y. We know we go a certain distance in the x direction and then a certain distance in the y direction. Let's say this is like 4 and this is like 2. So this then is the point 4, 2. And we can locate every point in the flat plane, so the 2D flat space, with two coordinates, an x coordinate and a y coordinate. All right, so the intersections of all these lines would make rectangles. So sometimes this is called rectangular coordinates. Rectangular coordinates. It's another name for 2D Cartesian or 3D Cartesian. Rectangular coordinates. All right, so what we're going to do today is talk about polar coordinates. So 2D polar coordinates. So 2D This should be 2D Cartesian. 2D polar coordinates. And to define polar coordinates, what we need to do again is specify an origin. So we specify an origin. So we'll say this is the origin. But now we have to do something else. We have to specify unit distance. So to specify unit distance, and then specify polar axis, i.e. theta equals 0 degrees, or radians. We'll just say 0 radians. So our polar axis is actually just going to be along the positive x-axis. So that'll be what we call theta equals 0 degrees, or 0 radians. And then every point in the polar coordinate system is going to be somewhere on a circle. So at theta equals 1 radian, we have another axis, or not an axis, we have another coordinate. Theta equals 2 radians, theta equals 3 radians, theta equals 1, theta equals 2, theta equals 3, 4, 5, and 6. And then for r, we have distances away from the origin. So theta, or r equals 1, r equals 2, etc. So in 2D polar coordinates, every point lies somewhere on a circle. So every point lies somewhere on a circle. So the points are described, or we describe points in polar coordinates with an ordered pair r theta. R is the distance from the origin, and theta is the angle rotated off the positive, or off the polar axis. Or the theta equals 0 axis. So you have like a different type of axis that you're talking about now. You have like a theta axis, which is like the rotation, and you have an r axis, which is the distance away from the origin. So if you're going a certain distance away in the r direction, where you're moving away from the origin, no matter which angle you're at. So it's a different way of talking about the two numbers that describe your point in space compared to Cartesian, but either way, you can get to every point in 2D space either by saying it's somewhere on a rectangle, or in this case saying it's somewhere on a circle. So if I just like highlight a point here in orange, and let's say it's this point right here, this would be the point 3, 1 in polar coordinates. So this is the point 3, 1 in polar coordinates. I move a distance of 3 away from the origin at the rotated angle theta equals 1 radian. So Any questions? Okay. So let's look at the relationship between the two coordinate systems. So relationship, there are other coordinate systems, but so far we've only talked about these two. So what is the relationship between them, between these two coordinate systems? So if we kind of plot them together, oops, say x is here, y is here, and then let's say we draw a circle, and we're talking about some point on that circle. Well, we know it has an x value, and we know it has a y value, and it also has an r value and a theta value. So this is r, and this is theta. So from trigonometry, we see a right triangle with a leg of x, a leg of y. So r squared equals x squared plus y squared. So that's the first relationship we want to note from polar coordinates to Cartesian coordinates, is that r squared is equal to x squared plus y squared. Another relationship that we can see is that r over x would equal cosine of theta, which we could say then that x is equal to r cosine theta. I'm so sorry. This should have been x over r. So x is equal to r cosine theta. So that's another important relationship. And similarly, y over r is equal to sine theta, which would tell us that y would equal r sine theta. So also important. And then probably the last one we really want to focus on is theta would be arctangent of y over x. But that would potentially only give us angles in the right half of the plane, because the range of arctangent is negative pi over 2 to pi over 2. So we could say plus pi as needed. So if you wanted to get something in the left half of the plane, you would need to add pi to whatever arctangent gave you. So that is those are our equations that relate the two coordinate systems. And probably the most important three are the first three that we wrote down. R squared is equal to x squared plus y squared, and x is equal to r cosine theta, y is equal to r sine theta. We're going to use all of those very frequently throughout this course. So keep those fresh in your mind. So they're going to be extremely useful. So I just want to plot a few points here in the polar coordinate system just to get an idea of where they are. So example, plot the points in polar coordinates. So we're going to assume that these points are polar coordinates. So the first one is 2 comma 2 pi over 3. The second one is the point -2 comma 5 pi over 3. C, or the third one, is the point 2 comma -2 pi over 3. And then D, the last one, is the point -2 -2 pi over 3. So we want to plot these 4 points. I'll just draw an axis for each one. So I'm drawing Cartesian coordinates, axes, but we'll plot the polar coordinate representation. So what does that mean, 2 comma 2 pi over 3? Well, that means I need to go from theta equals 0 to theta equals 2 pi over 3, which is like, I don't know, right here-ish. So I need to go to the angle 2 pi over 3, and then go a distance of 2 away from that origin in the direction of 2 pi over 3. So that gives us our point 2 comma 2 pi over 3. Whoops, sorry, the second one should be 2 pi over 3. I think I said 2 pi over 3, but I wrote 5 pi over 3. Sorry, so I'll make a change there. And part B should be 2 pi over 3. Okay, sorry about that. Now for the part B, we're going to go to the same angle, 2 pi over 3, and if it were positive 2, we would end up, up here. We know that that's 2 comma 2 pi over 3. Well, what a negative r value means is that you go the opposite direction. So you go back towards the origin, and you come out the other side, a distance of 2. So that gives us the point -2 comma 2 pi over 3. So it's like you're going in the negative radial direction. So this is the negative r direction when we're at 2 pi over 3. So 2 pi over 3, positive direction would be that blue point, and then the negative r direction goes the other way. And we go a distance of 2 again, but in the negative r direction. For part C, we go in -2 pi over 3. Well, that's just the opposite way. So it's a clockwise rotation. And we end up here. And we go out a distance of 2 because it's a positive value. And we end up at 2 comma -2 pi over 3. And then the last thing we need to do is go to that -2 pi over 3 angle and then go in the negative r direction for part D. So there's -2 pi over 3. But then we need to go in the negative r direction. So let me draw a dotted line for that angle. And then go in the negative r direction would put us back up here. And again, we go out a distance of 2. So this would be the point -2 comma -2 pi over 3. You might say, well, that's ridiculous. Why don't I just use a positive r and a positive angle And that's fine. It's just getting some experience with writing these polar coordinates. Most of the time we're going to use positive r values. Actually, from here on out we're going to use positive r values, but this is just to give you an idea of what a negative r value means, or how to think about a negative r value. So any questions about this example? All right, guess we'll just keep moving on. I got some questions here, so consider. You know, back in Cartesian coordinates, what was represented by the equation x equals 2? Well, if we drew some axes here, and we go over to x equals 2, so it's like 1, 2, that's the x and the y axes. What was represented by x equals 2? Well, if x was equal to 2, then it was just a vertical line. So the answer is a vertical line. We just have a fixed x value. We could say a similar thing for polar coordinates. So in polar coordinates, you could say what is represented by r equals 2. So you draw flat space and then fix r equals 2. So the distance is 2. The angle is unknown, or it can be anything, just like y was anything up in the vertical line. The angle here can be anything, so this is going to be a circle of radius 2. So the answer is a circle of radius 2 centered at the origin. And then you might ask yourself, I wonder what theta equals 2 would represent. Well, we already kind of gave that away with our coordinate system drawing earlier, so what is represented by theta equals 2? So we draw axis, or axes, and if we fix theta at 2 radians, then that will say that r can be anything. So if r is anything, theta equals 2 radians, that's like this angle right here. And it's just a straight line, theta equals 2, whereas this was r equals 2. So the answer here is if you fix theta and let r vary, you get a straight line. A straight line along theta equals 2 radians. So that's all that is. I do want to highlight one thing specifically. Note, if we had theta equals pi over 4, well, that would say that arctan y over x was equal to pi over 4. And so that would mean that y over x would equal tangent of pi over 4. And so y would equal x, because tangent of pi over 4 is 1. So that we can see is a straight line with a slope of 1, which is just the angle pi over 4. So I'll just draw that one right here. So that's just the line y equals x. In Cartesian coordinates. So sometimes you could get a nice Cartesian representation. Sometimes you can't necessarily get a nice, pretty Cartesian representation, like arctangent of 2 radians. That doesn't come out to be anything pretty. So, but I mean, it's still possible. All right, so let's look at some regions now, because this is basically what we're going to do most of the time in polar coordinates, is describe a region with polar coordinate bounds. So wouldn't really call this an example. I would just say it's like an exercise. So describe the enclosed region by specifying bounds for the polar coordinates r and theta. So a nice semicircle here. Let's say it's a radius of 2, and it's the enclosed region in blue. And then another region. Again, it's going to be a semicircle of radius 2, but now it's over here. And then we're going to talk about one more region. It's going to be a quarter of a disk. Between radius 1 and 2. So we want to specify the coordinates, or the bounds, for r and theta. Well, it looks like in the first one that r is going from 0 to 2, and theta is ranging from 0 to pi. So if we specify those bounds for r and theta, we are basically describing the semicircular region, or this half disk. Well, for the second region, if we say, okay, again, r is going from 0 to 2, but now theta, we would say maybe goes from negative pi over 2 to pi over 2. I like to use the smallest angles that I can possibly write. I probably wouldn't say from 3 pi over 2 to 5 pi over 2. I would say negative pi over 2 to pi over 2 to describe that region. For the last one, I would say r goes from 1 to 2, and theta in this case would go from 0 to pi over 2. So that's how I would describe that region with polar coordinate bounds. So any questions about that? Does that make sense? We're going to be doing a great deal of this when we get to double integrals and polar coordinates. So understanding how to look at polar coordinates on their own terms is going to be extremely useful and important. And describing the regions with these bounds is going to be extremely important as well. Okay, well, let's keep moving on then. This question, or an example, we'll say, whoops, I think we'll call it an example. Example, what is described by r equals 2 minus 2 sine theta? So what is described by r equals 2 minus 2 sine theta? All we can really do is maybe, I don't know, pick some values of theta and see what the corresponding value of r is. So let's pick different values of theta and try to find what the value of r is going to be. So I'm going to draw just 2D flat space here. And let's say I pick theta equals 0. At theta equals 0, r is equal to 2. So at theta equals 0, r is equal to 2. So this is the point 2, 0. Okay, well now let's say I pick pi over 4. So theta equals pi over 4. And r is equal to 2 minus 2 times square root of 2 over 2. So that's 2 minus square root of 2, which is about 0.6. So at pi over 4, my r is much smaller. So I'm much closer to the origin. So that's 0.6 comma pi over 4. And what if I pick theta equals pi over 2? I get r equals 0. Whoa, I come back this way. So far, our graph looks like this. Let's see, if we pick theta equals 3 pi over 4, we get r equals 0.6 again. So we kind of come back out this way. And if we pick theta equals pi, that'll be r equals 2 again. Let's back out here. And let's say we pick theta equals 3 pi over 2. We'll get r equals 2 minus 2 times negative 1, just 2 plus 2, which is 4. So actually our r value is actually much larger. So it's going to look something like this. And there is like an inherent direction associated with it because of the changing theta value. But this is what we call a cardioid, because it kind of looks like a heart. So it's a cardioid. So these polar equations, or these polar coordinates, can represent things that are a little more interesting than maybe just, Cartesian coordinates. We already know we can represent circles and things like that much more easily. well, now we can get shapes like cardioids and four-leaf clovers and all kind of cool stuff. So we'll get to those four-leaf clovers at some point, I'm sure. Let's look at another example. If we look at another example here, might say what is represented by r equals 2 sine theta. So what is represented by r equals 2 sine theta? So it's a similar equation, but not exactly the same. So I wonder what happens. So what we're going to do here is we're going to change to Cartesian coordinates. So change sine theta to y over r. Change sine theta to y over r. Then we get r equals 2 times y over r, which means r squared equals 2 times y. Well, we know what r squared is. R squared is x squared plus y squared equals 2 times y. And now complete the square. So I'll get x squared plus y squared minus 2y plus something. And what we're going to add is 1 to both sides to complete that square for y. So it'll be x squared plus y minus 1, quantity squared, which is 1. So it's a shifted circle of radius 1. Shifted circle of radius 1. So that's what this represents. And it's shifted in the y direction 1 unit. So shifted 1 unit in the y direction. And it has a radius of 1. Another example. What is represented by r equals 37 over 9 sine theta plus 28 cosine theta. So this looks pretty complicated, but it's actually not going to be too bad. Take a minute, make sure everybody's caught up. Alright, so what we're going to do for this problem is we're basically just going to multiply both sides by that denominator. So cross multiply the denominator. I wouldn't say cross multiply, I would just say move the denominator to the left. So move the denominator to the left. So we'll get 9r sine theta plus 28r cosine theta equals 37. And what is r sine theta? Well, that's just y. So this is 9y plus 28r cosine. Well, that's x equals 37. And this is just a straight line equation. So this is just a straight line. equation. It just has a different slope and intercept than we were talking about earlier, so. So just a straight line. Of course, I skipped a step there. Maybe I should make sure it's clear. What I did was I multiplied r by the denominator 9 sine theta plus 28 cosine theta equals 37. And then I distributed the r, of course. So it's kind of the step in between the white line and the blue line. Okay, cool. Any questions? Okay. Let's see what we want to do today. We'll finish up with this example. I don't know if I want to get into limits necessarily today or not. Functions of multivariable functions. Hard to say. We'll see. So I'll do one more example here. Probably, yeah, I guess I'll work it all out. So example, find the bounds of the region between the circles. And we have two circles. We want to be outside the circle x squared plus y squared equals 4, but inside the circle x squared plus y squared equals 4y. So what do these two circles look like? I guess I could represent them with polar coordinates first. So this is r squared equals 4, or r equals 2. This is r squared equals 4r sine theta, or we could say r equals 4 sine theta. So that's their polar coordinate representations, but now let's graph them. So r equals 2 is like this circle here. But what is the other circle? This is x squared plus y squared minus 4y plus 4 equals 4 by completing the square. So x squared plus y minus 2 squared equals 4. So it's a circle of radius 2 shifted up 2. So I'll just graph that here. This is 4, this is 2, and that's at center point. And then I want to stay between those two circles, so I'll just color it in orange here. So I'm trying to describe this region with some bounds for r and theta. Well, r is going to stay between 2 and the outer circle. So the inner circle to outer circle for r. So r is bounded between the inner circle, less than or equal to r, less than or equal to the outer circle. So inner circle is just r equals 2. The outer circle is 4 sine theta. So that's our bounds for r, or those are our bounds for r. But now, what are the bounds for theta? Well, theta seems to go from this value to this value, theta 1 and theta 2. So theta is between theta 1 and theta 2. And I wonder how we can find those values of theta. So where do the circles intersect? So where do the circles intersect? Meaning what angles? So what are the angles where the circles intersect? Well, if the circles intersect, they have the same r value. So r equals, well, I could say r is equal to 2, but 2 then would be equal to 4 sine theta because the r values are the same. So equate the r values. So get 1/2 equals sine theta. So what angle in quadrant 1 gives me sine equal to 1/2? Well, that's pi over 6. And then what angle in quadrant 2 gives me a sine equal to 1/2? Well, that's 5 pi over 6. So pi over 6 less than or equal to theta less than or equal to 5 pi over 6. And that's it. Those are our bounds for this region in orange. So the area, or the region between those two circles. Let's see. Do you mean... Okay, so Caitlin has a good question. What if we were talking about... Okay, this is just to address Caitlin's question. I think she's saying we have the circle here, but we also have the circle here. And I think what she's saying is, how would we find this region here? So that would be a little trickier. That's a good question, but would be a little trickier. We would say that until we got to this point, so this theta sub c, so for 0 less than or equal to theta less than or equal to the theta sub c, we would say r goes from 0 to 4 sine theta. And then for any angle from theta sub c, we'll call it theta c1 to theta c2, which we know already is pi over 6. So let me call it pi over 6. So then that's the first region right here, basically. And then for pi over 6 less than theta less than 5 pi over 6, I would say r goes from 0 to 2. And then from 5 pi over 6 to pi, I would say r goes from 0 to 4 sine theta again. So it's like you have 3 different regions you have to talk about. It's not actually below the axis the way I've drawn it. It's misleading. It's actually starting out right here. But I can't draw a nice pretty circle, obviously. Let me try to make this graph a lot better. I'm going to try to really be careful drawing the circles. want to draw the orange one first. And then the blue one second. And then these three regions. So it's like 1, 2, and 3. So 1, 2, 3. So you kind of have to break it up into 3 different regions because the bound for R is changing depending on what angles you're talking about for the what you're asking, Caitlin. You have to say, okay, R is going from 0 to the orange circle for angles between 0 and pi over 6. But then for angles between pi over 6 and 5 pi over 6, R is going from 0 to 2. And then from angle 5 pi over 6 to pi, R is going from 0 to the orange circle again. So it's basically like 0 to orange for the first little bit, and then from 0 to blue for the middle, and then from 0 to orange again for the last bit. And that's how you would get that small little sliver. That's a great question. Love that question. Other questions? Well, let me just confirm, was that your question? Okay. Sweet. All right. Well, I think we're gonna have to call it a day there. I'm not gonna start a new section with just like 10 or 15 minutes left. So, the exam is gonna be on Friday, and we will have an assignment on Moodle. I'll post a PDF of the exam. It'll open up Friday, 8 o'clock, and you'll have until 9:20 to work the exam, maybe even 9:25 to work the exam, submit a PDF using a scanner app of your choice for your smartphone, or if you're using OneNote or whatever, that's fine as well. Oh yeah, sorry, Caitlin had another comment that I missed. So we have to break it into circular sectors. Yeah, basically because the R bound is changing with your theta value. So the orange for the first little section, and then blue for the second section, and then orange again for the last section. So yeah, you have to break it into little sectors to get each little piece. So yeah, the exam is going to be Friday. It's going to be everything up to 12.6, which is what we did on Friday. And then polar coordinates and all this stuff will be on the second exam. I'm not going to put it on the first exam, even though I think on the schedule it's on the first exam. I'm not going to put polar coordinates on the first exam, so just a heads up. But yeah, it's going to be just an hour and 20 to 25 minutes, and then you have to upload a PDF of your work using a scanner app, or if you have OneNote or whatever you're using, that's fine too. So we'd be able to use a calculator. I'm not going to make anything like crazy where you need to crunch any numbers. So actually, let's say no calculators just to be consistent for the calculus sequence. So I'm not going to make anything like super, I don't know, number crunchy. It'll all be pretty theoretical. So like this example was very doable without a calculator. Yeah, we won't have time for review on Wednesday. We're actually, I wouldn't say we're really behind, but we're not on schedule, according to the syllabus. So I want to go ahead and get chapter 14 going. That way at the end of the quarter, we will have some time to review, hopefully before the final. So I have tried to slow down a little bit this beginning of this, our first exam. So we're not like, we've not really been rushing through, which is good, but that means we kind of can't really review either. So, but I have tons of videos on, tons of extra examples and things like that might help. And yeah, just Googling stuff, Googling, I don't know, other schools' exams is good. If you have my old exams, that'll be a good review, but I wouldn't use those as like, okay, once I work this exam, I'm going to be fine. I would work it as like, okay, how did I do on this exam? Not use it to study, but use it to just see how well you did. But yeah, so we'll say no calculators, just like I think it says on the syllabus. And then, yeah, it'd be Friday, 8 o'clock, 8 to 9:25, I think we'll do, 8 to 9:25. And then I'll grade them, get them back to you. I actually have a folder on Google Drive that I share with you, and then you'll see all your work in that folder as it gets graded. So, other questions? Okay, well, I guess we'll call it a day. I'll see you guys on Wednesday, chapter 14. We're going to start it up, and then exam on Friday. Happy studying. Have a good day. See you guys.